So good afternoon, everyone. My name is Alaaeldin, and I'm a senior engineer in AEDA LLC, Advanced Engineering Design Apps. Today, I'll be presenting the shear capacity of circular bridge piers confined with FRP wrapping. This work was done in cooperation with Dr. Haider Rashid at Kansas State University. I was lucky to be I was lucky to have Dr. Asad Ismaili in my committee in my master's and partially in my PhD. He also teach me concrete design, advanced concrete design, and structural dynamics. This picture is from the defense in the master's. And eight years ago, in my first class with him, he awarded me half points, extra points. He was always smiling. He was always helpful. And you can go to him at any time in his office, and he will be happy to help you. Continuing to the presentation, I would like to discuss the objective, what are we trying to do, and then the formulation, how we did it, and then the software that we generated to implement the procedure, as well as some results, and we ended up doing some parametric study to have a deep understanding of the problem, and then finally the conclusion. For the objective, the clear objective is to generate the moment shear force axial force interaction diagram for an FRP confined circular concrete columns, where Kansas Department of Transportation used it to apply to design the concrete columns piers when they confine it with FRP, where the FRP fibers is going as a hoop around the column. I would like to show a small animation on what do I mean, like through this objective. So if I may. I hope that you can see this window, the small animation. So this is the 3D interaction diagram, where the vertical one is the axial forces. This one on the left is the moment, and this one on the right is the shear. So looking from the vertical and the left one, this is the famous PM interaction diagram. And the objective that we have is to find what is the shear value on the third axis. So the main question is, because we know the moment, we know how to build the PM interaction diagram. But the question becomes, how do we know the shear, the corresponding shear for this case? So in order to do that, if I may, go back to the presentation. In order to do that, we decided to use the simplified modified compression field theory. And this decision was based on that the simplified modified compression field theory calculate the strain through tying the moment, axial, and shear strain in one equation. So the strain calculated through this method is the superimposed strain from the moment plus the superimposed strain from the shear and the superimposed strain from the axial. I'd like to introduce the simplified modified compression field theory just briefly, so we know how to implement it. This was introduced by Collins et al. In 2006, and just few assumptions they make that they have an effective section as dimension BV dV. In our case, for a circular, the BV is just the diameter, and the dV is calculated as the distance from the compressive forces to the tensile forces. Excuse me. It could also be taken as limits between 0.9 dE, which dE measured from the top of the section to the centroid of the tensile forces, or 0.72 H, where H is the whole diameter of the cross section. Also, a very important assumption in the simplified modified compression field theory that they assume that the geometrical centroid coincide with the neutral axis. So we have half of the section is a compression zone and half of it is a tension zone. and we have the tensile forces acting in the centroid of the tension zone, and we have the compressive forces acting in the centroid of the compressive zone. For the BV calculation, we have BV equal to the diameter of the circular section when you have a circular cross section. As I said, the simplified modified compression field theory superimpose the strain induced by the moment plus the strain induced by the shear plus the strain induced by the axial forces. So at the end, we have one equation that says that the strain at the tensile forces is simply the summation of these three terms: the moment term, the shear term, and the axial force term. So the formulation that we did to calculate the shear, as I said, the moment and the axial force is straightforward and we know how to do them. Then the question is, what's the shear capacity for the section for that moment and for that axial force? As the ACI do, as the Canadian standard do, as the AASHTO do, the shear capacity of the section is simply the summation of the concrete shear strength, the steel shear strength, as well as the FRP shear strength. For the concrete strength, it's 0.0316 beta square root of F prime C times BV dV. So we established that BV dV is the effective cross section of the effective transformed cross section that we have. Now, the key component in the VC equation is beta. Beta actually is an empirical factor that define how the diagonally cracked concrete will transmit tension through either aggregate interlock or double action, mainly the aggregate interlock. And then we have the VS equation, which is very similar to what we have in ACI, which AV FYT dV, the effective depth. And then we have cotangent theta. Theta is actually the key of this equation, and it's the angle of the crack, basically the angle of the inclination of the compressive stresses, or in other words, the angle of the expected cracks. And alpha is the angle of the transverse steel, if we have like inclined stirrups or even spirals. For the VF equation, we have the AF times the FFE dF divided by the spacing of the FRP. And the key variable in the VF equation is the FFE, the effective strain in the FRP. And I would like to start from this equation, the VF. The effective stress of the FRP through the NCHRP report number 678 is simply calculated through a reduction factor. So the strain, the effective strain, is just a reduction factor times the ultimate strain of the epsilon F of the FRP, which is epsilon FU. This reduction factor is presented in two equations. If you have a fully wrapped or you have a partially wrapped through discrete strips. This is the equation for a fully wrapped with an upper limit, of course, of 1 and a lower limit of 0.088. And it's a function in the rho F, the FRP ratio, and the modulus of elasticity of the FRP. In a very similar way, the partially wrapped is introduced with a lower value of 0.066 and a coefficient of 3 instead of 4. The rho F calculation comes for the discrete strips as 2 the number of plies times the thickness of plies times the width of the ply divided by the diameter in case of the circular section times the spacing of the FRP. For the continuous sheet, the width and the spacing are the same, so they cancel out, and we end up with 2 the number of plies of FRP, the thickness of the FRP divided by the diameter of the section. Going back to the simplified modified compression field theory. So we know what's the model for the FRP now, and we need to implement it in the simplified modified compression field theory. There are 2 cases that we have to consider. Either you have more than the minimum steel reinforcement, the transverse steel reinforcement, and we're going to call this case 1, or you have less than the AV minimum, and this will be our case 2. The AV minimum is calculated based on this equation, 0.0316 square root of F prime C BVS divided by FYT, the transverse yielding steel. And then going back to the beta and theta. The beta is the key component in key factor in calculating the VC, and theta is the key component in the VS equation. Both of them is function in epsilon S. Epsilon S is the longitudinal strain in the tensile forces location. We have beta coming from 4.8 divided by 1 plus 750 epsilon S, and we have theta as 29 degrees plus 3500 epsilon S with a limit of 75, limited from 75. And this is what I was talking about when I said that the strain and the simplified modified compression field theory is simply coming from the moment strain plus the axial strain plus the shear strain. So having one equation, we can utilize it to get the shear capacity of the section. And this is our goal. This is what we are trying to achieve. If for case 2, when you have less than the minimum allowed AV, we're going to introduce a reduction factor for the beta. And it's F51 divided by 39 plus SXE. SXE is limited, the minimum is 12. So this term is either 1 or less than 1. So the beta factor is always less than 1 or less than 1 when you have less than the required AV minimum. Theta equation does not change. And the SXE from the beta equation is coming from SX times 1.38 divided by AG with the aggregate size, the maximum aggregate size, plus 0.63. This is an empirical equation. And as I said, the limit is 12. So this value is always less than 1, and this value is always less or equal to 1 in case 2, when you have less than the minimum AV. If you have compression, as I said, the epsilon S is at the longitudinal strain at tensile forces resultant. If you have epsilon S less than 0, this is a compression condition. You are allowed to include EC in the equation. So you're including the concrete effect in the epsilon S equation. AC is just the area of concrete on the flexure tension side. So this is just half of the section. As I said, the simplified modified compression field theory divide the section into tension zone and a compression zone. And you only include the tension zone in this case. This is just briefly the formulation that we used, how we implemented it. This is the standard procedure. We start by deciding on what case do we have. Are we less than the AV minimum or are we more than AV minimum? And then we do an assumption for V and theta. And we calculate the longitudinal strain from the equations that has the moment, the axial, and the shear. And we get theta and beta. As I said, it's a function of epsilon S. Then we calculate V from VC, VF, and VS. And we keep the iteration till we converge. This is what I'm going to call a standard procedure. This is the standard procedure that we have been using. However, AASHTO have some limit that we have to include when we do the interaction diagram. First, the moment is always have to be more than VdV. So we are limited to VdV. The longitudinal strain, the epsilon S calculated, has to be less than 0.006. And then we have a spacing when the shear stress is less than 0.125 F prime C. The spacing has to be limited to the minimum of 0.8 dV and 24 inches. If we have more than 0.125 F prime C, this spacing becomes half. So we have 0.4 dV and 12 inches. And in a similar way, to avoid concrete crushing, the total V has to be less than 0.25 F prime C BV dV. This is just describing the whole procedure that we have. We start by defining our section BV and DV, and then define which case are we going to be, case 1 or case 2, based on the minimum AV. And then we get our longitudinal strain from epsilon S equation. If we are less than 0, if we are more less than 0, we can take the compression into account. Otherwise, we cannot take the compression into the account. We calculate beta and theta, and then we give the shear strength. Up to here, this is the standard procedure. And then we have to implement the limits. We have the limit where the moment has to be more than VdV. We have the limit that we have, the strain has to be less than 0.006. If not, we have to set the limit to 0.006 and recalculate. And then we have to check the spacing limit. If we do not meet the spacing limit, there is nothing we can do, and we have to change the properties of the section. And then we have to check if the concrete is going through a crushing or not. And we have to set, if so, we have to set our V to meet the concrete crushing criteria. This is describing case 1. And case 2 is very similar, except we are going to change the beta and theta calculation. This is just like a diagram, an interaction diagram for the moment on the x-axis and the shear on the vertical axis. This is for a constant P, for a constant axial force. We have, this is our standard procedure. And if we do not have the first limit, which is M has to equal to VdV, we'll be going exceeding the limit, like we are going straight in a straight line. However, we're going to flat plateau here because of the first limit. And typically we have a standard procedure for a while. Sometimes we don't even have a standard procedure, and the limits control the whole design. And we have the capacity coming from the second limits. And then finally, we meet our maximum moment capacity at 0 shear. We generated a software for Kansas Department of Transportation to implement this procedure. This is the force on this is the axial force, and this is the moment, and this is the moment, and this is the shear force at a certain axial force. This is taking into account the FRP properties, the VF, either partially confined or fully confined. Next, I would like to present some results that we have, and we compared against some experimental data. First, we have Kawashima 2000, et al. 2000. He has one layer of carbon FRP surrounding a cross section with F prime C equal to 4.35 and a spacing of the steel equal to 6 inches and relatively small axial force of 42. And we have a very good match. The shear on the vertical axis, and the moment is on the horizontal one. The point around this line needs a good agreement. If the point of the experimental is way in, then this is not a good agreement. This is saying that the interaction diagram does not represent the data. This is another unit for Kawashima et al. 2000, but he has, in this case, the same axial force, but he has 2 layers of carbon FRP. And then he has 1 layer of carbon FRP, but he increased the spacing to almost 12 inch, comparing to 5.9 inches in the previous unit too. And then we have James and Shamim in 2013. 2 layers of carbon FRP under axial force of 290 kips with a relatively high Fy of 72 KSI, and this is the cross section. For the second unit from James and Shamim, they have 2 layers of, instead of carbon, they have GFRP under the same axial force. And then we have 1 layer of carbon, but they increase the axial force to 430 and the same section and the same material. And here I'm showing the control column. And this is for 1 layer of GFRP under 430 kips. And then they pushed the axial force to 602 kips for 2 layers of carbon FRP and then the 3 layers of GFRP.
Alaa, you have 1 minute.
Overall, we have a very good agreement, with the experimental results. And then we did a very quick parametric study where we've had the cross-section diameter between 28, 36, and 44 inches, the steel ratios, the transverse steel spacing, F prime C, Fy, and the FRP plies. We have our carbon FRP and GFRP as a constant. We did not vary the properties of FRP. This is the effect of the diameter. We have 28 inches, 36 inches, and 44 inches for a ratio of 0.01 and 1 layer of GFRP. This is quite an effect. And then we have the effect of the steel ratios, did not show a great effect on the interaction diagram. This is for a 36-inch diameter cross-section with 1 layer of carbon. And this is the effect, and this is actually the highest effect that we have. It shows from the spacing for 2 inches, for 4 inches and 2 inches for a diameter of 28 inches and 1 layer of GFRP. This is the effect of F prime C for a 4 F prime C, 6 case I, and 8 case I. And then we have the number of FRP plies effect. We did not show a great impact of on the interaction diagram. It barely ranges between 260 and 280. In the conclusion, we studied how do we develop an interaction diagram, the moment, axial, shear, force interaction diagram, the 3D interaction diagram. And we validate this against some experimental results using the NCHRP report number 678. And I would be happy to answer your questions.